Unrehearsed, so I wasn't expected to be here, but I thought we'll maybe introduce, not the session itself, we'll introduce the background that led to this session. The discussion started, I would say, several months when Dr. Fadi Zahiri was invited from Intel to speak about the digital age and the role of big data and the role of the Internet of Things and the role of computing in the future of mankind. And that discussion evolved into human security and how can the new data science can help in promoting human security. And the second stage of that discussion was a follow-up to the WAFRA lunch. When we were talking about there's a lot of expertise in the data science on campus and there's a lot of interest in water food security. So how could we have a marriage between the two disciplines and emerge into something that can be useful to the human security factors issues from the knowledge of the expertise next door. So without any further ado of this background, I'd like to introduce the moderator of this session right on the spot. So thank you for being here. We're all here to learn, and we're delighted to venture into I think, a win-win engagement, I would say, not marriage. So I use this is an engagement of two disciplines that I'm hoping we can do something good for Lebanon and for the region. Thank you.
Well, thank you all for being here. I guess I just came out of class, that's why I'm running this way. And I thought I had actually a few more minutes. Thanks for Professor Mariette for letting me know that I'm actually late. So I missed the introduction. I just want to make sure everybody knows why we're here. We're having a very nice, hopefully, seminar series on transforming agriculture through the Internet of Things, artificial intelligence, and big data analytics. We're going to try and do this in a panel setting, so we will have the presenters share some of their own expertise, but would like it to be interactive as we get to the panel part. So I'd like to actually invite the presenters to join the table here, and then, as they come, I'll introduce them. So our presenters are actually, I'll start from the Faculty of Agriculture, Professor Hadi Jafar. So please, take your seat at the panel, Hadi, please. Okay, this is better. Okay. So as I mentioned, Professor Hadi is from the Faculty of Agriculture. His expertise is in irrigation engineering and water resource management. I'll have him talk more about himself. Our second speaker is also from the Faculty of Agriculture, Dr. Rula Bashur. Dr. Rula is a research associate in the Faculty of Agriculture and Food Sciences. She has a PhD in irrigation engineering from Utah University. I also give her a chance to give a more fuller introduction. Before I get into the two other speakers, we were supposed to have one more speaker from the Faculty of Arts and Science and Computer Science, Professor Fatima Salim. Unfortunately, she couldn't make it, and Dr. Rula willingly accepted to cover that part. From the Faculty of Engineering and Architecture, we have Professor Mariette Awad, Associate Professor in the ECE department. She has expertise in artificial intelligence and machine learning. And last but not least, the person who actually is behind getting us all here is Professor Mazen Saghir, also from the Faculty of Engineering and Architecture. And his area of expertise is in, among things, embedded system, Internet of Things. The way we're going to do this, actually, we're going to have each of our speakers come and present to us how AI can be used in agriculture, and how we can benefit also. I don't know if the WIFRA discussion came up. We'll try to bring up some specific discussion in the context of WIFRA and see also how AI can help for WIFRA, and what are some concerns we may have also from AI as it comes and help us in WIFRA. So without further ado, I would like to actually invite our speakers. We're going to go like 15 minutes each. we were going to start with introduction to AI, so Rilla or Mariette, or Mazen, you had some.
I can start with like just a brief overview of IoT.
Okay, so if you guys already agreed on the change, go ahead.
Thank you. All right, so can everyone hear me okay? Okay, so good afternoon, and thank you for inviting us to the Faculty of Agriculture and Food Sciences. I'm very happy to be talking to you today, not just because I'll be introducing the topic of AI and machine learning, but probably some of you don't know that I consider myself to be a son of this faculty. My father was a professor here a very long time ago, and I have very fond memories as a child and as a teenager running through these halls and on ERIC as well. So, this brings back some very nice memories.
Welcome home.
Thank you, thank you. But today I'm not here to talk about the past, I'm here to talk about the future. And what I'd like to do, for the next 10 minutes is maybe just give you a brief overview of what the Internet of Things is, and maybe just talk a little bit about some of the applications involving Internet of Things and machine learning, and then I'll leave it to my colleagues to tell you a bit more about the details. So you've probably already heard of the term the Internet of Things. What is the Internet of Things? Why is it gaining so much importance these days? So, as a definition, what is the Internet of Things? It's essentially a network of devices. And the device can be anything, pretty much anything, okay? And that device usually includes a lot of electronics, some software, some sensors, some actuators. Actuators are things like motors that allow things to turn on or off, as well as some communication devices that allow these devices to connect to networks and through those networks to other devices as well. And what this allows us to do is to have all of these devices communicating with each other and exchanging data and exchanging information. So just to make the idea a little bit more concrete, you've already probably heard about smart homes. Okay, so one of the things in a smart home you might find is something like a smart thermostat. What that device does is it can obviously measure the temperature inside the home, but also it can contact a server, a weather server, to see what the weather is going to be like over the next few hours. And based on that information, and more importantly, based on information that it has learned about your preferences, it will set the temperature accordingly. So this is an example of an Internet of Things device. So why now? Why have Internet of Things devices taken off all of a sudden? We started hearing about IoT over maybe the past 10 years. So why now? Well, several factors. One factor is the abundance of computing technology. So you may or may not have heard of Moore's Law. Moore's Law simply means that transistors, which are the basic building blocks of microprocessors and microcontrollers, are getting smaller and smaller and smaller. And this means that the processors themselves are becoming smaller, and they're so small these days that you can essentially embed them in any object or any device. Same thing for communication technology. So the communication and networking technology today allows us to connect all of these devices at fairly high rates, very high speeds, very high bandwidth. And again, this allows us all of these devices to communicate with each other. Again, you might have heard the term cloud computing. So the idea there is a lot of this data that's being sensed is being sent to a massive data center somewhere, it could be half away around the world, and the data is being stored there. And more recently, there's an interest in, okay, we have all of this data, how can we extract some useful information out of it? And this is where machine learning and data analytics come into play, and this is where my colleagues will tell you more about it in a lot more detail. So that's why now? So IoT is touching pretty much every aspect of our lives today. So any device, as I said, can be embedded with an IoT device and mainly can be used to monitor and manage that device. And agriculture is just one of the areas that IoT is touching, and we're going to talk a little bit more about that in detail. So what's the impact of IoT? Well, according to the World Economic Forum, it's nothing short of a revolution. So if you think of the late 18th century, the late 1700s, this is when the steam engine came into being, and this created essentially what was known back then as the Industrial Revolution. So people's muscles were now replaced by machines. Fast forward a little bit later, so around the 1870s is when we started witnessing electrification. And this allowed us to have a lot of factories, and again, with electricity, coupling electricity with mechanical force, again, this led to mass production and essentially the mass production of objects or commodities. Around the late 1960s, this is when transistors were first invented, and this really sparked the revolution of information technology, so computers, communication technologies. And as I said earlier, this has led to all of this miniaturization, and today we're at a point where we're talking about things called cyber-physical systems, systems that connect the cyber world, computers, communications, to the physical world. And the physical world, again, can be essentially anything. So here are some examples of some of these cyber-physical devices. So we talked about the smart home and the smart thermostat. You've probably already heard about self-driving cars. So we have cars that can sense their environment using some very high-resolution radar systems. They're called LiDARs, that can map in 3D the environment around them, and through machine learning, they can identify, let's say, pedestrians versus other cars, and they can drive and essentially navigate through busy streets with other vehicles, with other pedestrians, and so on. We have drones today, so these are, they call them unmanned aerial vehicles. So, most people think of, they're just taking pictures. That's, a big function of theirs, but they can also be used, as we'll see, in agriculture to do things like remote sensing and gathering very precise information about, let's say, the state of growth of a crop, about the temperature of the soil, about various factors that are important to agriculture. We also have smart grid or smart energy technologies. So all of these are examples of cyber-physical systems. So what will the farm of tomorrow look like? So the farm of tomorrow is going to be precise. It's going to involve a lot of precision agriculture devices. What does that mean? It means that if we want to irrigate, we will irrigate very precisely. We'll only give enough water that the plants need. If we're going to spray pesticides or herbicides, again, we're going to do that in a very precise manner. This will lead to more efficient use of resources, less harmful effects, and obviously it'll be a little much more economical to run a farm, especially when natural resources are being more and more scarce. So I just want to give a few examples of agricultural applications of the Internet of Things. So here are some applications from crop management. I'll just go over them very briefly, and then you can read the slides on your own later on. So for example, with crop management, if we have the ability to measure various aspects of a crop, then we can also manage it. So we can do things like yield prediction. We can try to predict how much yield we're going to get from a certain crop based on certain measurements. For example, you can count fruits on a tree, maybe using some image processing techniques. You can estimate things like grassland biomass, either through remote sensing techniques or other techniques. You can detect diseases. So again, using some image processing techniques, you can visually, using smart algorithms, tell whether a plant is diseased or not. And weed detection. So if you're trying to determine whether a plant is a weed or a crop, again through image processing and artificial intelligence, you'll be able to detect whether this is a crop that you don't want to destroy or a weed. Okay, for animal science or livestock management. So again, we can manage the livestock, the animals on the farm. So think of this as using like a Fitbit on an animal. So you can now get all sorts of information about the health of the animal, and you can even predict how the animal is behaving. What are they doing at any given point in time? And again, this will help you understand their behavior and their needs. In terms of productivity or production, so whether it's milk production or eggs or poultry, all of this, again, with the appropriate sensors and the appropriate algorithms can be used to improve yields and improve productivity. Water and soil management. So water is a very scarce resource these days. So again, it needs to be managed very properly, and a lot of work has been done on evapotranspiration estimation. And again, our colleagues in agriculture will tell us about this in a lot more detail. So these can now be estimated on daily, weekly, and monthly basis. And finally, for soil management, you can do things like evaluation of soil drying, estimation of soil temperature, and so on. So to end, I just want to give out a call for action. So why are we doing this seminar over here? Well, AUB, I think, is very unique in the fact that it has a farm, it's operating a farm, and this is a great opportunity for us to try and perhaps model this farm as a futuristic farm and try to apply some of those technologies that we'll be talking about today and really develop a model farm in the Middle East that can be used to solve our own problems. So we have our own problems in terms of the climate that we are in, the scarcity of the resources, and so on. So perhaps we can try and apply some of those technologies there. We have the expertise at AUB, so within the Faculty of Agriculture, within the Faculty of Engineering, Arts and Science, Health, Medicine. So we have a lot of expertise to tap into, and myself and my colleagues are with the Faculty of Engineering. We just represent a very small group of faculty from engineering, but we have other colleagues in other areas that can also play a role. And finally, you are the domain experts, we are the technologists. And there's a nice saying by Mark Twain, it says that to a man with a hammer, everything looks like a nail. So we need your help to try and help guide us a little bit to see exactly what we're trying to solve. We just love to throw machine learning at essentially every problem. So we need your expertise to try and help to guide us in order to come up with some useful applications to these technologies. So I'm going to stop here, and I'd like to hand it over to my colleagues. I guess we'll be taking questions during the panel, right?
That's right. Thank you, Dr. Mazen. So we're going to switch actually from engineering to agriculture, and we're going to have Professor Hadi share with us some of the successes in applying AI at AUB for agriculture. Yes, go ahead, please.
Thank you, first of all. Very interesting. I just want to add the expertise I'm great in the faculties. We also at IT are also looking at IoT, and so please include us. Absolutely. We'd love to help you. Thank you.
Well noted.
I'm going to start with saying that we can do nothing without the IT. Good afternoon, everybody. It's my pleasure today to talk about the application of smart irrigation and the interlinkages with the engineering work. So as Dr. Saghir mentioned, it's the future. I will be also playing the role of the devil's advocate in some of the cases because we can make a clear picture that, smart irrigation and IoT and machine learning is the solution to our problems. But I'm going to go to the nitty-gritty details of what challenges do we have and how can we encounter them based on some experiments and some studies we conducted at AUB here and also at ERIC. So I will be focusing on smart irrigation. What you see here is a smart greenhouse with all the technologies of sensing outdoor climate, also sensing plant and soil moisture, indoor climate, equipment control, remote management, computers, machine learning, to produce finally a crop. Now imagine our farmers applying this at their greenhouses. I mean, how long do we take to take our farmers to that level? This is something that we also need to address, which I think is missing from our webinar, the farmers' adoption aspect, but it's something to keep in mind. So we hear the word smart irrigation all the time, but what is smart irrigation? As you all know, and smart irrigation is when you irrigate the water when needed, so on time, and also with the right amount, with the right system, in order to achieve some objective. The first objective, of course, is to optimize the yield, reduce the water use if possible, minimize the energy, and optimize or maximize the quality of the product. So maximizing the yield is not only the objective. Sometimes we don't want a maximum yield, we want a better quality. So it depends on what you're planting. But who is leading nowadays in this aspect? For sure, the United States is leading in the world on food production. Average tonnage per hectare for cereals 7.34 for the United States versus 3.7 for the world. So they're doing something that makes this better than other places. Now, how to do smart irrigation? I think we need sensors for smart irrigation, and I will talk about these types of sensors in a bit. And smart irrigation is not drip irrigation, by the way. So it could be other types of irrigation. Mostly drip irrigation companies advertise for drip irrigation because they sell products, and they want to sell these products and increase the use. So you can use drip irrigation, but not necessarily you're doing it in a smart way. So smart irrigation, based on our experiments, it's promising, but it's not always a success. And I will explain in a bit why it's not a success. Now, if you look at sensor types for smart irrigation, we have different types of sensors. We have ground sensors, so sensors that you put on the field or in the field, also in the soil. You have meteorological sensors, and you can also use remote sensors. The ground sensors, they can be soil-based, that is, they sense the soil moisture, and they can also be plant-based, so you put them on the plants to sense the moisture in the plant itself and detect the stress in the plant. Meteorological sensors are also used to calculate what we refer to as evapotranspiration. You can also have infrared sensors to detect the temperature of the leaves remotely for you to infer also the water stress, of course, before it happens. Remote sensors include a variety of sensors nowadays. You can have drones. In the past, they used to have aerial imagery. They're still done also with LiDAR techniques. But we also have the satellite sensors, and satellite sensors are really a big topic. I'm not going to cover them today as much as I would love to, but it needs more time. Examples of plant-based sensors are the sap flow meters. Here you see a picture of a sap flow meter measuring the transpiration on a corn plant. And one of our graduate students, Gatson, he did this summer at ERIC. And we measured the water stress effect on the transpiration through these sap flow meters that work by heat dissipation. And you can get results of how much water the corn plant is transpiring every day. In this case, it was using about 1 liter of water per day, one plant. So you can also use infrared sensors. In the picture, you see what we call a thermal map. So it's a map of surface temperature that you can also use to detect water stress. Soil-based sensors can be of different types. We have volumetric sensors that measure soil water content by volume. And in the figure here, you can see that the sensor can be connected simply to a controller, and the controller would be connected to an irrigation valve. And once the water threshold in the soil drops before a user set value, it will trigger the valve to open, the pump to operate, and then you irrigate. And while you're irrigating, the sensor is logging soil water data. So when the soil water reaches the level that you desire, you can also turn off the valve and stop the irrigation. In this way, the problem is solved. We irrigated when needed, and also we irrigated the amount that we needed. Now, the situation on the ground is much different than what appears here in this picture. And I will show you the data. Why does that happen? Because there are issues with sensors. And what are the issues? The first issue is the location. So where do you put the sensor? At what depth in the soil? at which part of the field, how close to the root zone. And this varies depending on your field soil, right? So soils are heterogeneous. Also, the plants themselves are heterogeneous. There are natural variations. So you might be putting the sensor in a place where the plant might have a disease, and then it will not be using water, so the soil moisture would be high. So you won't be irrigating, while other plants might be using water. So this doesn't show up unless you have multiple sensors. And now this takes you to the question of how many sensors do you put to get a representative value. Also, sensors need calibration. As you see here, the available soil water varies by soil type. So suppose a sensor is reading 20% by volume. Do we irrigate or do we not irrigate? Any volunteers? Excellent. Thank you. So as you see here, a 20% soil moisture in clay soil is below permanent wilting point. So the plant is already dead, while a 20% soil moisture in a clay loam soil is near field capacity. So you have to know the soil type. And the soil type also varies not only horizontally in the field, but it varies vertically. So you have different layers of soil. So all of these needs to be taken into consideration when you use sensors. Now one might say we can use this sensor, the PR2 delta T probe, which is multiple layer sensor, and this is very good, but the price of this sensor is $1,200. Other types of sensors are potentiometric sensors, which measure the energy of water in the soil. And these can also be connected to data loggers and to controllers. But they also have a problem. What's the problem with these sensors? Is the response time. So once you irrigate, the soil will get saturated, but before you get the signal, before there is this equilibrium with the sensor, you will not get a signal that the soil is saturated until after 15 or 20 minutes sometimes. And in these 15, 20 minutes, you will be extra irrigating. So you'd be losing water. Other types of sensors are meteorological sensors. Now these are lovely for research, and we do have some of them at ERIC. But these sensors also have their own challenges, because these sensors do not measure water use. They calculate water use, and they calculate water use based on physical equations, and the equations or the calculations are as good as your measurements and installations. So you have to install the station in the middle of your field, in the middle of a homogeneous field, far away from any land that is not irrigated, far away from any fallow land, to get representative values of water use. Else, it will be recording wrong results. So these also have to be carefully selected and carefully planned before you can assume that it is good to use them. There's also a problem with these, is that they measure the potential ET, or they calculate the potential ET, or the potential water use. They do not measure the actual water use. What you need to measure the actual use, if you want to transfer these results to other areas that are planted with different crops, is the crop coefficient. And the crop coefficient varies according to variety, according to local practices, according to the density of the field, according also to the growth stage. So these are also locale specific, and they need calibration. However, a lot of studies rely on meteorological sensors to calculate water use and to tell when to irrigate. So we come to the remote sensors. Remote sensing can be of two types: passive remote sensing or active remote sensing. Active remote sensing is when you have radars. So there's an instrument that sends electromagnetic radiation, and based on the reflected radiation, it measures water use or soil moisture. One challenge with this is that it only measures soil moisture in the top 0 to 3 or 5 centimeters of the soil. It doesn't penetrate deep enough in the soil to tell you the root zone soil moisture. Other types of sensors that are optical sensors, they are of high advantage because they can cover large areas of land with one shot. You can talking about here about thousands of kilometers, square kilometers. But these also have challenges. For example, if you have clouds, you don't get any data. You only see the clouds. They don't penetrate the clouds. They also have problems with the cost if you want high resolution data. And high resolution is always needed when you have small field sizes, which is the case in our country and also in our region. However, you can use drones, because sometimes if you have clouds, drones, you can fly them below the cloud level, and you can get data about your crop, about the water use, about the thermal signature, and so on and so forth. What's the problem with drone-based sensors? Is the explanation of the results. So farmers cannot interpret the data by themselves. They need experts, like Mazen, like myself, like Mariette, to interpret this data. And by the time you download the data and you send it to the farmer, there is a time lag. There is also a cost, right? They have to pay the price for this expertise. So this is also a challenge. So speaking about case studies, what you see here is the same field with different resolutions. So this is a field in the Bekaa Valley. Who can guess the crop? So this is a 0.4 meter image. So it's the highest available commercial resolution image that we purchased for the Bekaa. And still, with this high resolution image, 40 centimeters, you cannot tell what the crop is, because it's very difficult to distinguish the spectral signature of the crop, even using the highest resolution multispectral sensor. You need hyperspectral data to do that. And this is where machine learning can come in. But you can see here, this is the greenness or the NDVI of the field. Based on this is a rapid eye, 5 meter. You have to pay. 30 meter, it's freely available. And now we have Sentinel-2, which is 10 meters, which is freely available. This is 1.2 meters spectral, which is word view. You have to pay $25 per square kilometer, minimum order of 100 or 25 square kilometers. So this is the NDVI, and this is a cannabis field in the Bekaa. And it's irrigated with which method? Who can guess? Very good. Surface irrigation, excellent. So you can see with surface irrigation that the greenness increases down the canal. There's a canal here, and there's more water coming to this part of the field than this part. And you can detect this using the NDVI and also the leaf area index calculated from the NDVI. So here, there is an advantage to these types of sensors. From LAI, you can calculate also the crop yield. So ground sensors, we did an experiment between 2014 and 2016 on this crop. What is this crop? Za'atar. So this is also remote sensing, but using your camera on the field, right? It's still remote sensing. You can detect this crop. We planted it at Eric. We also planted it in the greenhouse. And we have a lot of machinery here, worth of like $3,000 of sensors and loggers and controllers just to plant Za'atar, imagine. This is the logger. I had to learn a lot about electricity and also about communication. So this is the protocol that we implemented at Eric. So it's basically hands-free operation. So we had a small weather station communicating with an air card, and the air card communicates with the GPRS network, the touch. It sends the data, and also this communicates with the controller. And based on the calculated evapotranspiration, the controller will trigger the valve to open and close. We had also to get a relay to switch on a pump, also automatically. So when there's an irrigation trigger based on evapotranspiration, you open the valve, you turn on the pump, you irrigate, and then when you're done, it will automatically shut down by itself. So this was working for around 3 months. And not only this, you can also access it from your smartphone or from your desk computer. And this is the interface. You can look at the programs that you have, the zones. You can also get the weather at Haushesned, which is Eric. You can get how much you irrigated. And using this, we were able to come up with some response surface of the optimum water use for our crop based on calculated yield, as you see here. Not only water use, but also nitrogen use. So this was a success story at Eric. The greenhouse data involved, I'm closing in 1 minute. The greenhouse data involves several sensors. And you can see here that different sensors respond differently. Some sensors register 10%, while other sensors register 20 or 30%, depending on the calibration. And also you have on the secondary axis the plot of the soil water potential using a tensiometer, which also has its own lag time. So this has also its disadvantages. On your left, you would see how different models that calculate evapotranspiration give different results on the same crop for the same field. These are 3 models, metric, pi, CBEL, and this LXC. And this is also in the Biqa. And these are wheat and potato fields. And you can see how the ET can vary from one model to another. So which model to use depends on your validation. So validation is extremely important to calibrate these models before you can input it to any smart or IoT system. So models differ, and so do sensors. So you have to be careful when you use any of this technology. I can skip this slide, but for IoT, we require infrastructure, hardware, brains, mobility, and connectivity. Thank you, because I exceeded my time.
We obviously will not have enough of you, Hadi, so we're going to have you back again. Now that we've heard actually from Dr. Hadi and Dr. Mazen about the application of our agriculture, and we've heard at different times the mentions of machine learning, the next stage of our panel or presentations is to bring us all at the same level of discussion. So what is machine learning? What can it do? What is artificial intelligence? So Professor Mariette will start, and then followed by Dr. Rula on that discussion. The floor is yours.
Thank you, Hazem. Good evening, everyone. So I'm going to try to really speak after the 2 great presentations we had so far, and I'll focus mostly my presentation on AI and big data. You heard about IoT, you heard about the applications and how we are not living up to the expectation of the requirement from agriculture, but let's try to see what is AI. We don't want to put more, we don't want to draw or dump more stuff on AI and big data than it can handle. So what is AI? Anybody wants to volunteer? Artificial, yes? Artificial intelligence, yes. So it's artificial. By definition, an artificial thing is something that is not natural, so it's going to be deployed or executed on a machine or a computer. And intelligence, this is where we face really a problem, because we don't have yet a good and systematic definition of what is intelligence. This could be combinatorial, it could be more at the emotional level. So let's just try to say it's an ability to learn, to cope, and contemplate, think, and reason. So basically, when we as like technologists or engineers, we talk about AI systems, so basically we want a system that can perceive the environment, and for agriculture would be the environmental, maybe the crop type and all of these things, define a certain course of action to maximize a very specific goal that this system was designed for. So with that, we would like to simplify the systems that we can create as being either something that can think humanly or act humanly. Or maybe, because we don't want the irrationality of humans, we want to create an AI system that can think or act rationally. So it depends on really the end goal this AI system is being created for. So is AI now a new thingy? No, but it's suddenly now everybody is aware. Everybody wants to really be on the wagon of AI and machine learning. It's a field that started back in the 1950s. It's a very dense chart here, and most of the systems that were reported are more from the engineering side, so very few as in terms of agriculture or IoT kind of per se devices. So back in 1950s, the field started with a Turing test saying, if you can create a machine that can fool a human by not being a machine, then you would have created an intelligent machine. That was the first test. And if we were to look nowadays at all the AI systems that we have, very few would really pass this Turing test. So from the 1950s to the 1966, a lot of effort from the AI community was there to really design this strong AI that would be the equivalent of a human brain in terms of processing, decision-making, and the like. But the field was not really moving fast enough and not to the level of all the information that the scientists wanted or the venture capitalists back then. And there was a big period that we will coin as AI winter from the 1966 until 1977. And then this is suddenly the field is back on. It's as if you watered your plant, and we have one of the first systems from IBM being able to play against a chess champion. And since then, every now and then, we hear of big systems from AI competing in international competitions against experts and scoring well. So now that we know that the field is not new and this winter AI is over, so let's try to understand where we stand in this environment. Are we to be concerned that AI is taking over tomorrow or in a year's time or in the near future? So this is a triangle showing how we would like to divide the AI stages by being a machine learning, and these are the stages of systems that you have experience with in your daily life, such as Siri or the Alexa and the like. And then there is the second stage, which is the machine intelligence, and this is where currently our technology is. And then the tip would be the machine consciousness. And this is something that many labs or many research is heading into, and this is what we term as strong AI. And this is where the field started, but up to now, we cannot say we have strong AI. We're more on the lower part of the pyramid, and we have a lot of weak AI systems that are out there, and they make our life easy and very comfortable. So why is the winter of AI over? I think Mazen has described it when he was talking about the IoT and the cloud. The way I would like to refer to it is the trinity. It's this combination of hardware that's becoming very affordable, and when we talk about hardware, it's anything from really your cell phone, this is a hardware, your wearable is a hardware, the cloud, the data centers, and the fog computing and all the like. So the first element, the ingredient why the winter AI is over is because I have really reliable, cheap hardware that I can access. Then the second ingredient is the big data. I have tons of data that is collected from social networks, from sensors, from environment, biometrics, bioinformatics, and you name it, financial. And the third and last component are the algorithms. The algorithms are not something very new. I will get to this in a later stage about deep learning. This is the big buzzword now, but this is not an invention that was, or this is not an algorithm that was developed a couple of years ago. It was around, the proofs were around, but the hardware was not able to really execute on the complex algorithms in combination with the big data that we have. But now we have these three, so we should be able to really leverage them to make a better future for everyone. So I touched based on, and I threw in a couple of terms here, AI, machine learning, and deep learning, and we hear them. Are they the same or are they different? So basically, the best way to really look at it is to consider them subfields of each other. AI is the big umbrella, and this is the one of the title in our series of webinars here. So AI, and then machine learning is a subset of AI, and deep learning is the other subset. So basically, deep learning is whenever I am producing a system that relies on consecutive levels, so a little bit very similar to the brain, how it reasons and how the stimuli goes from the different layers to reach really the decision making. And when I talk about machine learning, is any system I can produce that is able to learn without being explicitly programmed. And now, even under machine learning, we kind of distinguish between two maybe styles, is the shallow and, I'm gonna try to use this. So the one that shows in here is a traditional machine learning flow where I have the data, I do some hand engineering, but by hand engineering doesn't mean that I will have to extract it manually. I can write routines, but me as an expert, I do embed my knowledge, guiding which specific features I would like it to be extracted. And this could be using machine learning. But the idea here, difference between a traditional and a deep learning, or the common now learning approaches, is that the features are decided before, and then I move forward with my system. And over here, this is what the deep learning is doing. It's like, give me a lot of data, and then from this data, I do a good representation between the output and the input, and then I give you a system. So I'm going to give you a simple analogy here. So traditionally, you have, in programming, you have the data, and you have a certain program, a certain outcome you want, and then you use your computer to produce the output. When you talk about the machine learning environment, you have the data, and you know the output, or you would like to have a certain output. Then you use these two to produce the program that eventually will be used on yet-to-be-seen examples. Or, also in a different way, so assume that we're talking about an agriculture environment, and I want to use the old way, a knowledge-based machine learning environment. So I could say if the moisture of the soil is this and that, then this would be the action I would like you to take. And probably in agriculture, you do already have such systems, probably not very affordable, but the technology is there. What you would like, the new way, is to just have a self-learning program that would say, you know what, try to classify soil moisture and then change the settings, whatever, to reduce the discrepancies between what I'm getting and what I should get. So for me to achieve this using machine learning, what is the field there to offer? There are different types of learning that could be divided according to this chart. Somebody can argue we can divide it as shallow or deep. These are just different ways of division, but this division over here is basically capturing the dependencies between the input, output, and the goal of the machine learning. So we do have the simplest or the less complicated machine learning approach is what we call as supervised. So basically, my data is labeled. I have this picture of the field, and I know it is, let's say, for potato. So this is very well identified. It could be noisy, it's fine, but at least the label is there. So in that particular case, the machine learning is doing just like us. It's basically memorizing. I have a task, and I need to be able to predict the label, knowing that I have seen few examples. Another type of learning would be the semi-supervised, where not all of the data is really well labeled. So I have a set that is well validated, well understood, and I have some wild data. So in that particular case, when I'm developing my machine learning, I'm expecting my machine learning to do some reasoning. So it's more like get from the environment some input, then fine-tune and move forward to fine-tune your model. So this is what we call as an online learning. And finally, we have the unsupervised. I have data, just figure out something for me. And this is what we expect as in terms of understanding. So over here, you're determining some groups, you're trying to do some clustering. So these are the different types of learning that you can have, and depending on your application, you do choose which one you want to go and adopt. So technically, when we talk about machine learning as a field, we have three major knobs that we have to be very careful about. We have the representation, or what we call that, what are the different models, the different families of machine learning I can use? What's the type of evaluation, because this is very important. I want to make sure that I have the right utility function, the right scoring function for that. And finally, it's about optimizing. I really want to make sure I can evaluate all possible options and really land on this optimal solution for me. So I want to talk more about the representation or the allowed models. Machine learning is very rich in terms of the techniques that it offers. So this is by no way a complete listing of all approaches, but at least it captures most of them. So you have the family of deep learning, and I will present another slide with just more visual about just deep learning. We have the ensemble, where I have weak learners, and I run my decision across different types that I don't tune too much, I don't optimize, and then I just do some aggregation from their output. We have the neural networks, we have regularization techniques, system expert-based, regression, and decision tree, Bayesian, heuristics, and you name it. So specifically for deep learning and neural networks, because now it's the buzz, this is a chart that really tries to visually capture the different developed machine learning techniques specifically on deep learning, and what's the relationship between the input and the output, and how are the autocorrelation and the mechanism of the feed forward and the feedback happening with respect to the also type, because this neural network is trying to mimic the unit that should compute information the same way we do. So would it be a spiking neuron, or it's just like aggregation? So you have different neurons with different types of summing and performance that are used in neural networks and deep learning. So let's go back and recap in terms of this machine learning. If I really were to dilute it, at the end of the day, I am after this function here, the red one, right? So I have the input, and I have a certain output, and I want my machine learning to learn this F so that when I have a new data, I should be able to predict it precisely. So a supervised and an offline, where I get all the data at once, would look like this. So I have the training data, I try to do some pre-processing, I have my model, my new data comes in, I'll be able to spit out my final output. So as machine learners or as data scientist people, we have multiple questions we should ask ourselves about. Can I find a Y? What's the best way? What would be the best F function to use? What type of pre-processing? How should I prepare my X? Okay. Okay, so I have to go fast. So how should I fill it, and how should I find F? I should be done shortly. So in summary, so that was a snapshot of what machine learning is like from very high-level things at a hyperspectral, not at a drone view. So we as engineers, we think that agriculture needs disruption, because for obvious reason about the sustainability and the cost associated with producing all the food and the security. This is probably a very old way of farming. Currently, we have already some equipment out there, some sensors to help the agriculture industry, but we want to take it a bit out from the farmer and rely more on the central insight data that should be provided by machine learning. And this is where we hope we can help to identify more what type of data you have. If you train one system, how can you do transfer learning to another system? And what would be the best selection model you can have. So basically, how we can help, or at least I'll speak on my behalf. So we have developed a lot of machine learning algorithms that take into consideration specific characteristics of data, noisy, incomplete. It needs to compute very fast. It's documented in multiple databases. We have done some multi-agent systems that just operate on their own based on some inputs, and they maximize their scheduling and their tasks. And we have a couple of publications along the 3 axes of the AI winter over kind of thing on improving algorithms, on hardware, and on big data. And thank you. I ran over my time.
So this will take us to the last presentation of the speakers, and then we'll move into what I think is the most exciting part of today, which is the panel discussion and opening it for interactive discussion. But we'll give Dr. Rula the floor now, and then we'll go to the panel after that. Please go ahead.
Okay, thank you. Good afternoon, everyone. I'll try, as Dr. Haj mentioned before, I'm presenting on behalf of Dr. Bousalem. She was not able to be with us today, so I hope I will give justice to her presentation. And I'll try to be on time, okay, to allow time for questions. So I'll go fast. I will start with something that Dr. Saghir mentioned at the beginning about smart homes or smart cities. When we talk about smart cities, probably you've heard a lot about this. So it's when we have, I don't know, for example, for waste management, we have garbage cans, they are connected, they tell the hauler when they are full, and then somebody comes and collects it, okay? So we have maybe smart buildings that tell when it's time for maintenance, and then we do this. So, and all these things in smart cities is based on AI and IoT, okay? And and big data, what we've been talking about. But also in agriculture, we have AI, okay, and we can use AI. And as mentioned in the UN summit in 2000, so it was declared that AI will be eradicating extreme poverty and hunger, okay? So we hope so. Okay, so why do we need AI? So we all know that as per the FAO, in 2050, we will have 2 more billion people on this earth, okay? And eventually, to feed them, we need about 70% more food. But only we are expecting 4% growth in the productive agricultural land. So we should produce more food. So how is this going to happen? So definitely, we have to be more efficient with farming, okay? And how to be more efficient. So one way of being more efficient is what we talk about when we talk about precision agriculture. So maybe some of you, the agriculture background people, know what is precision agriculture. So it's basically using the drones and the sensors to get some data. And then the data will be analyzed, the model using the machine learning, the AI, and then this information can be used by the farmer to make decisions for monitoring their crop, his crop, and managing the fields. I will give some examples on applications. So we'll talk about the automated agbots. So agbots is robots in agriculture. So these are enabling farmers to increase their productivity. An example of agbot is, for example, harvesters. So they can be automated harvesters that they can detect the maturity, for example, of an apple, and then they will harvest the ripe apples, okay? They can also have, I think, I don't know who mentioned, Dr. Saghir probably mentioned about the detection of, they have algorithms to count the number of fruits on these. So by knowing how many fruits we have, the farmer will be able to manage his productivity. He will know how much yield he will have and then how to manage the yields. Another example is farm beats. Farm beats is actually something that was developed it's an AI application that was developed by Microsoft. So what it does, it's technically an end-to-end IoT platform for agriculture that puts AI and machine learning at its core. So how does this work? So what's the idea is, in many places in the world, the farmers, they don't have internet on their fields, right? So you don't have, most of the time, the farms are in remote areas. You don't have internet access. So what they did is they took waves from the radio, the TV waves, okay, or what we call the white TV waves, okay, and then they used it to increase the Wi-Fi connectivity. So, and then they can also convert the big data into smaller size from gigabytes to kilobytes, if I want to say it the easy language, okay? And then using this low-cost connectivity and sensors and drones, they combine to develop what we call the precision maps. And Hadi showed some examples of precision maps. So if I want to show some of the end results, what we can have, in this picture, you can actually, I'm going to use the pointer. So in this field, this is the original field. The white dots are the sensors, okay? And then you can see they are not really distributed in a standard way. And this is because of what Hadi was mentioning. So for example, we have difference in soils, so the selection of the location of the sensors was based on the soil type, the different characteristic of the field. And then from using the farm beats, we can produce maps, okay? So these are precision maps. So for example, here we have moisture maps or pH maps. What does this tell us, okay? So for example, if you see here, this is the moisture map. So the white part is the wet part, okay? Being the wet part, that means this area do not need irrigation, while here we need irrigation. And this is where we can apply variable rate irrigation, okay? So instead of applying water everywhere, then we can know in the field where we can apply the water. Same thing goes for pH, okay? So this is a pH map. So again, agriculture people know that the use of fertilizer is really dependent on the pH of the soils. So sometimes we need to apply more fertilizer or depending on the pH of the soil. So here in this, seeing these maps, we can tell where we need to apply the nutrients. Okay, so this is an example of the farm beats. So again, based on some of these examples that I talked about, we know that agriculture is seeing to be needing the adoption of AI and machine learning. I'm not going to talk about machine learning. Mariette already talked a lot, so I'm going to skip these slides. Why do we need ML machine learning, and what are the types? So I have a smaller classification, not like the ones you showed. So I'm going to skip these and talk about the scope of AI in agriculture. So, for example, in AI, we talk about cognitive computing. So cognitive computing, in particular, is ready to move this technology. So what it does, it understands, learn, and then respond. Okay, so this is the concept of AI and machine learning. So it has to understand, learn from the data, and then respond to the situation we have. So I'm going to present five areas where AI is mostly applied in agriculture. Okay, I will again try to be brief. So we have the growth driven by IoT. So Hadi talked about the use of sensors and remote sensing. So in this case, we can use the proximity sensing, or what we call, or what is the sensors. So this is why we call proximity sensing. And remote sensing, the combination of these will help taking decisions. For example, in soil testing, soil moisture, so all these irrigation decisions, okay? Another field of application is basically the image-based insight generation. So that with the help of drones, we can have information on field analysis, crop monitoring, scanning of fields, and all this is by computer vision use. So some of the applications of this computer vision is, for example, disease detection. So disease detection, because Hadi showed the NDVI, so the vegetation index. So not only it tells us about the crop stage and health based on water, but also it tells us if we have diseases or if we have nutrient deficiencies. Okay, so we can tell where we have nutrient deficiencies, for example. It can even know on which leaf we have the disease. So it will apply the pesticide on the infested leaves, but not everywhere. And this is, again, part of the precision agriculture, where you don't want to just spray the whole field, okay? So this is, another one is about the crop readiness and identification, about we mentioned the maturity of the fruits, and other field management from irrigation, fertilizers, and all these applications. Another field is actually the identification of optimal mix for agronomic products, which is, with the help of AI and the machine learning, we can get to a point where, given all the data that we have on the field and the weather, we can tell the farmer, or the model can tell the farmer, what is the best crop to be planted this season, for example. And this is based also, if we can add also market data. So it will combine all the conditions of the field, the characteristic, and the market data to tell him what is the best crop to grow on your field in this area, on this particular area. Another application is the health monitoring of crops. So I also mentioned some things about the diseases, so to detect where the diseased plant, the deficient nutrients, and it will help us how to apply fertilizer in precision. Another thing is the automated technique in irrigation. I'm not going to talk about it. Hadi talked a lot about in his presentation about irrigation. So AI can be used also to monitor irrigation. So far we know that drones are important in agriculture if we want to do precision agriculture. One, to, for example, produce the maps, the precision maps we talked about, for aerial spraying, for crop monitoring, for management of the crops. So all this is needed. The concept of precision farming is to apply at the right place, the right time, to the right product. Okay, so this is, in summary, what it is. So I'm just going to skip this. Okay, and then we need a lot of technology to achieve precision agriculture, to basically achieve efficiency, sustainability, and profitability. So another example about plant stress using precision farming. So the same concept, we have the identification, classification, we predict and we classify the problem to come up with solutions. Robotics and digital farming, it's combining also, again, the sensors, the AI and the computers to recommend solution to achieve higher yield and better quality and sustainable production. Hadi mentioned some of the challenges he has in the adoption of AI or Internet of Things. So I will add to these challenges also, as it was mentioned also by Mariette, maybe in the engineering, they achieved a lot in machine learning. Machine learning is helping them with a lot of solutions. We are still not there with agriculture. We still need a lot to do because we have a lot of challenges. And some of these challenges are, for example, the lack of familiarity with the machine learning solution. We also have the exposure to different climates. So when we talk about agriculture, even sometimes if the planning is perfect, we have everything in place, but then you can have an extreme weather condition that will change the whole prediction that you had made. So there are challenges in agriculture that maybe are not there in engineering, okay? And then another main problem is basically that machine learning, they need to be trained. Okay, so Mariette mentioned about training of this. And training needs a lot of data. Unfortunately, in crops, we have one-time harvest sometimes. Okay, so we have one data per year. And this is not enough, okay? We also have, even with drones, we can have maybe more, we can fly the drone whenever we want. However, when we have large-scale agriculture, we are relying on satellite data, and satellite data have temporal resolution. So we cannot have the satellite coming over every day. So there are a lot of challenges in application of AI in agriculture, and we have to be aware of them. But hopefully, with the help of the engineers, we can get somewhere. Okay, thank you. Was I on time?
Thank you, Dr. Rilla. Thank you. Dr. Hadi, Dr. Mazen, and Dr. Mariette. So this actually, I think, is the best part of the panel discussion. I have a few questions of my own. I'd like to make myself useless, so I'd like to actually turn this around to the audience and have the audience actually ask questions. Okay, but I just want to, before I turn it on, I just want to put some context to the discussion. And again, sorry I missed the first couple of minutes actually, But I mean, the panel is part of this transforming agriculture through AI, IoT, and stuff. But I just want to mention the bigger context of WIFRA. I don't know if it was discussed earlier or not. Yeah, so I just want to mention, again, this hopefully will channel the questions. I feel we're in a very exciting time, both from a technology perspective and from, an agriculture perspective. I'm trying to remember who mentioned it. I think Rula mentioned about the Sustainable Development Goal. I mean, this panel helped me understand. I'll just read this, actually, for those of you who, may not have read it before. It was adopted by the United Nations in 2015, and it says, actually, they recognize that ending poverty and other deprivations must go hand in hand with strategies that improve health, education, reduce inequality, spur economic growth, all while tackling climate change and working to preserve our oceans and our forests. I take this actually and come to us here at AUB, and I read again from the WIFRA, which is aiming at the nexus of water, energy, health, and I just again briefly mention that the resource gaps facing the MENA region, including access to water, food, energy, nutrition, and healthcare. So I just want to put this in context, actually, that this discussion, may have little solutions to little things, but there are actually awesome opportunities for bigger things where, all these things come together, and hopefully we can make, this, extreme noble impact to humanity as a whole, and, talk about food security and all the, amazing things we can help in the world of WIFRA and agriculture. So I'll turn this floor to you. Hopefully, the floor is open to ask anything about understanding what AI can do, to how AI may actually mess with everything for us, or what are the problems we want to solve, and so on. Go ahead, please. If you can mention your name.
Hello, everyone. Sarkis Kabougjia. I'm the head of internal audit for UNIFERT in Lebanon and in the Middle Eastern countries. Actually, I'm not an agronomist. I just have a general question concerning the farmers and our challenge in implementing AI for the farmers in Lebanon. It's a general question. I believe farmers have a lot of illiteracy in Lebanon, and they have limited financial resources because the government doesn't give enough support, price fixing, protection of farmers from imports of other agricultural produce from other countries. So basically they have liquidity issues and they don't have government support. Plus, if the agribusiness companies will provide integrated farm management consulting, if you say so, to implement AI in their fields, how are they supposed to pay for them? This is one. Two, even if they were able to pay for them, who is going to help them in implementing a strategy, an action plan, a decision matrix? Okay, we received very wonderful presentations. I mean, if we want to go in the field and take action, who is going to do all this? I mean, financially, my main focus is on the finance part, basically, and farmer literacy. Thank you.
Thank you for the question. Who would like to try and answer? Okay, that we can do that. Okay. Hopefully, I'll remember the questions.
My name is Mahmoud Al-Sulah. Currently, I'm the vice chair for the high-level panel of experts for food security and nutrition. This is a global committee. Formerly, the Director General of ICARD here. One thing which is really very, very important, and I'm glad these topics are now really being pushed, is the fact that natural resource degradation is the biggest problem that is facing food security and nutrition. This is in the developing world particularly, and Middle East and North Africa in particular. Now the challenge is how to produce more with less. And this is really the big challenge. I like very much what you said, Dr. Hadi, that the drip irrigation does not necessarily mean efficient water use or less water. I can give quickly two examples. One is a broadbed farrow in Egypt, was started on wheat. It is now being implemented in 500,000 acre where it saved in wheat only 20% of the water and 30% more wheat. The other one is in Uzbekistan. Simply, this is surface irrigation. Every other farrow irrigation would save 30% of the water, and it will keep the yield as it is. So I think the challenge with what you are talking about, coming back to your point, which is very, very important, how can we help the small farmer with all this efficiency and smart agriculture to achieve more productivity with less input, which is really the key issue that I want really to emphasize. Thank you.
Thank you.
Thank you so much. I apologize, maybe the time will not be enough to engage in further discussion. But let me say that this is the beginning of the journey that I hope we can learn and move forward. I'd like to challenge the panel, and not necessarily now, but moving forward, in the general framework. Dr. Saghir, you mentioned the framework, which is the machine and the Internet of Things. I'd like to introduce the human, because that's really the biggest challenge. We focus only on technology development, though this is not necessarily the main issue. It is one of the issues. So let me give you an example, building on what was presented earlier by UNIFERT and by Dr. Salah. And we talked about it earlier. The optimization could be a solution where the optimization for the whole system, if you exclude the human factor, maybe go counterproductive to our SDGs. We talked about the best, if you look at the best sustainable agriculture, food, could be to increase the prices of food, but that negates the whole purpose of access to food. So my biggest challenge for us as a whole is how do you introduce the human factor and looking into the decision making that allow us to meet our future goals. We seem to be fixed on technology, and I think this is one of the puzzles and the pieces, but there are much bigger issues that we need to introduce. The human factor in decision making when it comes to multiple complex system. The other thing that we also missed in agriculture, how could we especially in this region? I mean, Hadi knows that most of our technology is coming from the north. We looked at hydrologic models coming from the north. So how does AI help us understand? This is a very complex system. When you talk about Wafra, how could we frog leap the years of lack of data, lack of understanding of the processes? How can AI help us understand first? So let's not put all of our basket in technology development, and let's really allow us to do two things: understand the complex system, to start the whole understanding. Second, how do you introduce the human factor into the complex Internet of Things, where at the end of the day, SDGs is about human security. So how do we put human security at the center of that revolution? And I think we're up to great things, and I hope this discussion continues.
Thank you.
Hypothetical scenario. Let's assume you have your AI system set up and it's doing everything it's supposed to do, and you've optimized it, and one of the farmers in Ba'a is now using it, and his neighbors, they don't know what it is, so they've decided to wait and see what happens. And the system comes up and says, okay, zra flayfli, because there's not going to be a lot of flayfli next season based on, I don't know what data it gets from our government. And the guy goes out and puts $1 million into flayfli, and بيجي على السوق يصرفون بعد ما يخلص الموسم, and apparently everyone else has decided to grow flayfli too without the system knowing. So الزلمة أكلها والميات اللي وفرون ما وفرون والسعر صار بالسوق بالأرض. So how does him having the system at that time give him the competitive edge he's supposed to have if no one else knows what he's doing? course.
Yeah, we're going to try and answer some questions at the end. Just want to do maybe a couple more correct, and then we could try to answer them.
Fadi Nafa, Program Manager Agritech of Veritech. Just one point to be added of what been discussed. Having more production, and we need 70% food production increase by 2050, but currently we have between 33 and 50% of food produced wasted, going to trash. So really, as it said before, understanding what's happening now, the complexity, how humans are interacting with technology is really important because indeed the resources are being scarce year after year, but also we're wasting a lot while going on that road. Thank you.
Okay, thank you. How about we do this? There's 6 questions. I'll start with the first one, and then see who wants to pick it up, and then we could, if you guys remember the questions, you can pick one and go with it. So the first one actually was from UNIFIL about, sorry? Okay. UNIFIL. It's about farmers having limited financial resources in Lebanon specifically, and so they have liquidity issues and lack of government support. Who will pay for all the resources that they need? Who will help in their strategy? Anyone wants to take that one? Hadi, go ahead.
I think this is a very important point, and that's what I raised in my first 1 minute of my presentation, that the farmer's adoption is missing here. How can we understand how quickly the farmer will adopt? Now, who will pay? I think the farmer should start small. So not with this big drone and multitudes of sensors and complex and higher companies. He should start small. For example, let him first get a controller. How many, you sell controllers at UNIFIL, right? So how many farmers have bought controllers? I think it's a very, very small percentage. So we're not even at the traditional machine system in agriculture, let alone the AI. So I think the farmer should start small at his scale, and then he will evaluate whether it will give him a payback or not, based on the small investment. And as the farmer learns by himself, okay, there's a learning process for the farmer also, before the machine. So as the farmer learns that technology can have an advantage, he will then try to invest and go to a higher level. And you are right, there are farmers who don't know, I won't call them illiterate, but who don't know how to use this technology. We don't know how to use technology. Exactly, but there are also hero farmers that you have to identify. And you know these hero farmers because, I mean, I have farmers coming for me, asking me to propose a smart irrigation system for them, and they farm at large scale, and they are in Lebanon, so they are there. So they also can be the training for the trainers, so they can lead. Now, finances is a problem in Lebanon, so. Yes.
I want to say, like in Lebanon, urban farming and hydroponics is the smart agriculture nowadays in Lebanon. It's available, but for field crops, it's still not available for smart agriculture. But hopefully still, labor in Lebanon is very cheap, so nobody's going for machinery which is used in northern countries. So I think that's why, but you should look into hydroponics and the urban agriculture where the smart agriculture can be used.
Okay, let me just move to the next question. I know that we could add more, but the next question kind of relates. So was from Mr. Mahmoud. So it was about sorry, Dr. Mahmoud Salah. Sorry. حفظ الألقاب للجميع. So there was a follow-on question, how can we help the small farmer and how to produce more with less? That's, I think, the essence of the question.
Maybe I can just give an example. So I don't know if you remember, I talked about something called the Farm Beats. Okay, so this was developed by Microsoft, and I didn't mention that what they are doing. So they are working with 175 farmers in an area in India. They are small farmers. Okay, and they were able last year to increase their yields by 30% while using less water and less nutrients. And this is but I mean, this was funded by Microsoft, so I don't know who is going to fund it for us. But so the idea was, the purpose of these, for example, applications is to produce more using less. And this is what we all want eventually.
If we want to talk about the challenge of increasing food by 60%, certainly the focus should be on small farmers, because 80% of the production, particularly in the developing world, is coming from small farmers. So small farmers, and I agree with you, mostly illiterate farmers. And this is where I think the big challenge that we really have to, okay?
Can I add something just on the previous question? I think there's a role for us also as maybe researcher or universities, and Hadi mentioned something about the application on the phone where you can see things. So we can have some pilot plots where we are recording moisture and we have weather data, but then we can maybe get to a point where we are just sending a text message to a farmer to tell him how much he wants to irrigate and when to irrigate. So it will be very low cost eventually, but I mean, somebody has to fund the whole system to be produced, but at some point. There are, exactly.
I think this is also, one of the things that we can distinguish ourselves globally in addressing these kinds of problems. I mean, all of this technology is mainly a Western technology geared towards major agricultural, producing countries, whereas our countries tend to be the small farmer without the access to the technology, or with where funding is a barrier. So our challenge is to try and bring this technology, maybe simplify it, make it accessible and cheap. And this is not necessarily just a technological problem, but it's also one involving finance, involving education, reaching out to the farmers and so on. So in addition to the technology, we also need help through outreach programs, through just educational programs to try and show people, the impact of this technology. But I think once those farmers are able to see the impact of this technology, hopefully there'll be, widespread adoption, and there will be quite a lot of impact.
I'm hesitant of adding my own value, but I just thought of recently, we in the Faculty of Engineering got, the luxury of going to Stanford and get involved into what's called design thinking. And I think this discussion, to me, with AI, with agriculture, fits very nicely into this design thinking process, where the focus starts by understanding the obstacles and the problems. So I think actually the first step in helping the farmers is actually going and talking to the farmers and understanding the problems that they are facing. And then, I suspect we will be amazed how many opportunities there are that we may not be thinking of. Instead of thinking, we have an AI, let's see how we can help them and let them, let's see if they can see if it's good. I think that the step actually, to me, is a little bit reversed. Going to the farmer first and understanding their problems, and then figuring out what solutions we can provide them. And I think some solutions could be low technology, and some of them could be, with high technology. Yeah.
We have to start with the farmer and end with the farmer.
Exactly.
With whatever we do.
Yeah. Unless there's more, I want to move to the challenge that the next one that's the biggest challenge that was put on the table, and then we have one more to discuss. So the next one was placed by Dean Mukhtar, and this is something that I personally had a discussion with him about, but how do we introduce the human in the framework? It's a very complex system that we have to deal with, from the farmer to the energy to the water to the health, And the question actually, how do we, optimize, optimizing, putting the human at the center of this. I mean, including the discussion we just had. It starts with the farmers, ends with the farmer. So, and it ends with the people consuming and, and so on. So, thoughts on this big challenge? Maybe I'll just throw the other part of this actually. Maybe we could discuss both of them. And how does AI help us understand and leapfrog, to understand the complex system that we have to deal with? Go ahead.
Indeed, this is a very challenging, question and statement. It's a big thing. But what I can say is that back to what I mentioned a bit in the presentation, machine learning. When you talk about machine learning or AI, let's just make a little bit more concrete description. So when I develop a machine learning or a system, I need to have a specific goal. So if I'm on the good AI part, so putting the human into the loop should be an intrinsic part of my machine learning and my system that I develop. So I will start with the farmer because this is where I get the data from. My system should be broad enough, prone to really identifying where is the bias and what's the limitation of the decision that they make, so that maybe I'm just moving forward to the question that we got here. So what if this AI gives me the wrong decision? So eventually, when I design my AI, I should be open enough and factor into consideration all these constraints, and they will be part of my system. So I have a lot of probably technologies developed in the northern territories. There is something in machine learning I didn't mention too much here, except that it was on one of the slides. There's something called transfer learning. So should we start from scratch in all these systems? We probably don't have to. We can have some of their technologies, some of their outreach, but we need to really contextualize it because we definitely have a different environment, different soil, different financial perspective. And I think just moving forward a bit with the interjection of Mazen, what we have here at AUB and probably in Lebanon, we have really a good brain resources where we can develop something more to contextualize. So I don't really need to have this consultant that is from blah, blah, blah company that would charge me an hour $100 when in our country, right, $100 is probably a week's pay from somebody. So technology should not be tagged with expensive dollars, and especially IoTs. I mean, IoT, the sensor that was mentioned by Dr. Hadi, to 1,200,000, right? So this is huge. The electronics, I used to work for IBM, and it was always an internal discussion that we have. A chip packaged, traveling from the US back to China, being encapsulated and with the pins and just ready to hit the market, is less than 10 or 12 cents. And it's a very important chip, let's say, in a phone. So if I really look at the individual component in a phone, the bill would not be even $60, and it's selling for a couple of hundreds. So we have to be careful when we talk about AI and systems that are whole built and they are very expensive, is because to really cover all the engineering costs and the fails and whatever. So we don't have to start from scratch. We can just leap forward, try to really be very selective. We have tons of approaches we can adopt with education from the technologist. From the farmer, we can probably produce a more tailored a solution that is affordable and having the human in the loop and the well-being of humanity there.
And just also add to what Maria said. So, I mean, like Maria said, the cost of hardware really is really very, very cheap these days. So there's no reason why we can't get, let's say, NGOs involved, perhaps to build open source devices and really get the price down. I mean, this is something, but again, this is back to the human factor. It's not a technical problem. It's really a problem of vision and bring the right people to do the right thing. I think if you do assemble the right people, you'll find that the technology is quite affordable and quite accessible. It's just a matter of how do you bring it to the farmer.
I'm not sure if we really answered the question, but I think it will be followed. I'm sure there's many discussions to be followed. So let's move on to the last two questions that were placed on the table. So the one, sorry, I didn't get your first name. Omar. From Omar, Omar was, wondering, we have this farmer that we've convinced to actually use the AI system. They spend so much money on the AI system. Her or his neighbors actually go do, something different, and the AI system doesn't know about, and all the investment goes to waste because the neighbors were actually just competing in the same realm without investing, right? Is that?
If one farmer does it and the neighbors don't do it, how does the machine know
what the neighbors did?
Know what it's not supposed to know, but it should know it? Because it will create volatility, and volatility is the enemy of AI.
Yeah. Well, let's.
I'll start and then I'll leave it to the machine learning. Okay, this happened. I used to work for Uniford in 2000, and farmers at that time, they were mainly on the coastal area of Lebanon planting citrus. And citrus at that time was not doing good. So, and there were some farmers who were moving to bananas. So farmers were cutting their citrus orchards, planting bananas because the banana price was high. And suddenly more farmers started doing that until all the farmers in the plain were planting bananas. And there was a banana problem. The price went down. So the AI system would be able to predict that if the human component, as Dean Muhtar mentioned, is brought in, because the system should be complex enough to capture and to forecast the human behavior.
If everyone does it.
No, not if the system would think that, okay, the system would optimize the plantations for the farmers in order for the price to be good, okay, for all crops. The system would not tell all the farmers to plant flayfly. Exactly.
We have to pick.
Of course, the system would pick.
I think this is a strategic decision to make, which AI is not at that level yet. AI is today at tactical or practical or instant point.
AI can look at trends, because not everyone's going to cut
Yes.
the citrus orchard and plant banana overnight. You can forecast trends how.
I would say machine learning would look at AI. Would look at the trends. But AI will be able to make your decisions. So one of the slides that I saw where these robots are trying to do some deliveries, this is decision. So this would be a different maybe approach that I would have to solve, to reach. But back to over here, I mean, we have to be careful. When I say AI is really a big umbrella, but I have to be specific. This AI system was built based on this assumption and to serve this goal. So if this hypothetical example that you gave, and unfortunately you had invested into an AI system that is not really robust enough, good enough, well studied, well engineered, then yes, بتاكل الضرب مثل ما كنت عم بتقول انه you'll plan the flayfly and it's the wrong decision. But you should be able to evaluate the same way when Dr. Hadi was mentioning they picked up some sensors were not able to give anything significant, and some sensors were able to. So this AI, think about it as a doctor or as just a regular farmer, right? You have these expert people in their field and they will give you the right decision, and then you have these other people that are not so much expert and then they will give you a non-optimal solution. So it really goes back, you as a user, you have to make sure that whenever you are adopting a system, you understand and you know that this is solid enough and you use it within the context it was developed. And we as engineers who are producing these systems for the users, we have to make sure that we design them to really fulfill the goal that we claim it's going to be doing. So it's kind of as if you go to a doctor and he gives you the wrong or the prescription, right?
So this is what your AI system did to you here, because it was not supposed, or it was designed not to take real input. It was just designed offline. I learned this, and this is like one-way prediction or decision making. It didn't go through the process of the online, the incorporation of current trends in the market, and fine-tuning of the solution. So I'm not sure if I was able to clarify well this thing for you.
Okay, so did you want to add more on on Omar's question before we go to Hadi's?
I can just add something really quick. Mariette mentioned, she talked about machine learning and how it is, for example, supervised learning, okay? So, and it's not like before we used to have a computer program where it's set, this is the computer program, so data and then output. But here with the machine learning, so it's data driven, right? So you have, and it will learn as you go. So for example, if you have such mistakes, okay, you will plug it back into your model and then it will learn from it. So it will, the predictions, okay, exactly. This is where before we go commercial, this is what we were saying, we are still at early stages, and this is what I mentioned. We are very early stages to make decisions, to make it out there for the farmers. They cannot bear the costs, right? So,
Amar, you know, I just want to add one final. So in this particular example, Anna, I think AI didn't fail because it was as intelligent as a human, right? So it ended up saying, plant pepper, and all the others farmers were planting the same thing. So the decision was right. If you take it as a single shot, not really inside really the human in the loop and a very well-designed AI. Look at it from that perspective. Yes. لا بس انت قلت رحت على الماركت كلهم كانوا زارعين pepper. ما كيف هن قرروا؟ لأنه it means they did an analysis and they ended up saying a farmer optimizes, right? So you decide what you want to use in your land.
Okay, we have one last one to actually discuss, and we'll maybe try to have a closure on the panel discussion. So the last one actually was a comment by Hadi. Fadi? Okay, Fadi, sorry. So Fadi's comment actually was that today there's about 30 to 50% actually of food that goes to waste. We're talking about, producing more and, making things more efficient. What about this issue? What can we do to actually address this particular issue? Who wants to take it?
So I'll address this from technology point of view. So the fact that we have waste means that we have overproduction. It means that, the production is not really tuned to the needs, to the actual needs. So again, here we can rely on, machine learning or artificial intelligence to be able to detect our exact needs and, convey that information to the production cycle. And here, let me just make a slight, tangent that, we're all here talking about machine learning and artificial intelligence. But even us as technologists, we realize that machine learning and artificial intelligence is not a silver bullet, right? So there are some disadvantages to the technology, and many of them are related to humans and human behavior, which AI still has, a long way to go before it can do that. So, again, the fact that we're having overproduction, I think, is a symptom of the fact that we have, systems which are not necessarily precise, that are not tuned to the actual needs of people.
I think what you talked about is very important. There's a lot of waste. Now, whether it's overproduction or something else, that's another story, because we know that there's waste that's inevitable. There are post-harvest wastes at the field level that you cannot escape. There are also wastes at the home when you eat and you leave something in your dish. There are a lot of wastes at the restaurants. Most restaurants, they trash like 1/3 of the food. So there's a human component who can control it, but we can say that at the farm level, technology can minimize waste by bringing, for example, machine learning into the harvesters, for example. So there are. Yeah.
Our startup, for example, was working on reducing spoilage waste in the supply chain.
Exactly.
And cold waste. So I fully agree. And what you're talking about is an answer to this
I think we went beyond the planned time for this. We were supposed to stop at 5, it's 5:20. So I want to thank the audience for their engaged and spirited discussions. I also want to thank our panelists and presenters, and I give everybody a warm hand, and thank you everyone.